So chapter 11 is pretty short. It's all about display mode. So I'd say let's go right into it. Basically, here's what you're seeing historically and currently on your screen when you're an ultrasound technologist. You have A mode, which we'll go into, but basically it's amplitude mode. B mode is brightness mode, which you're more familiar with. And then you're probably also familiar with M mode, which we'll talk about each one of these. So for amplitude mode, this historically was really the start of ultrasound. The analogy is that you send out one messenger, goes one direction, and that messenger brings back all the information from that one path. So it has two axes. One is amplitude and one is depth, which, as of course you know, means depth into what you're imaging, the patient typically. And it's described as a dot moving across the screen at a constant speed, so something like this. So very ancient in terms of computer technology. So I'll show you a little bit of an image there as well. Now your textbook has some excellent examples of these, so my suggestion is that as you go through this video, which of course you can pause at any time, that you're turning in your textbook as well, which is a practice a lot of you do. So because of attenuation, which again leads to loss of energy overall and loss of signal information, the further away the reflector is, naturally the smaller the spike is going to be, and of course further away indicates depth. So you have to take that into consideration. This is really good if you have a need for non-caliper depth. So again, this is old technology, but it had its purposes and it had its advantages. When you have a couple peaks, like a skyline here, as you can see, it's very easy to tell the depth, the distance between those two. And on the x-axis, that's where you had the reflector depth, and anything on the y-axis, which would represent those peaks of the skyline, that would be the actual amplitude or the echo strength. And you can go through multiple reflectors, multiple membranes even, and you could see various spikes for each one, and you can measure those distances. So nothing new on this slide here. So here's a great example. You can see at reflector A, between reflector A and reflector B, we have a very discrete, which means pretty much for our purposes easily discerned peaks. And so we could very easily tell what the difference in depth is between these two peaks. Again, attenuation has a say in reflector strength, but when we're trying to look at depth, this was useful. So B mode goes back to our grayscale imaging, and it's really the foundation for all grayscale imaging that we currently use. And you have different amounts of light displayed on the screen. We'll learn a lot more about that when we look at the instrumentation in later chapters. But on the x-axis, that of course was depth. And on the z-axis, that is the amplitude. Z-axis means into or out of the screen. So if you have a piece of paper in front of you, let's see, here we go. Piece of paper, if you have black dots on it, then that means that it's flat with the screen. And if you have anywhere between gray to white dots, depending on if you're in grayscale, then you are out of the screen somewhat. So that is your z-axis. And we're not going into the screen in this case. And you're familiar with the x-axis as well. It's what you would typically see. So if you have a strong reflection, think back to A mode, you have a strong peak. Well, in this case, you have a brighter pixel being that little piece of the screen between black and white. And on brightness mode, there wasn't really much resolution there. So here's just a little review, reminder of what the z-axis is. And this will become a little bit more understandable when you get to explore sector sizes and those types of things. All right, so here's a basic example. This is 256 Shades of Gray, which always gets a good laugh since we've had so many wonderful Shades of Gray references in the literary field. I'm sure they're wonderful. Not something I'm going to explore. Anyway, the difference in brightness is obvious here. And this is something that you're pretty familiar with from the scanning time. And then M mode is motion mode. Sometimes you might think of it as movie mode or moving mode, but basically it's looking at a pulse line and then you're continually keeping track of the reflector depth. And so you've seen this, I'm sure, in some way. I've had a lot of experience in the cardiac side of things, and I see this all the time. I'm not, of course, a physician or technologist for it, but I've had the patient experience for one of my sons, so you get to see these all the time. And so your y-axis will shift if there's motion, and if it's something that shifts a lot and periodically, then you'll see a nice oscillation back and forth. And x-axis now is time. So you're really looking at depth over time. So here's a simple example. And you can see that certain layers, certain reflectors rather, along the line are not moving, nice and static over time, and certain ones are. So this could be a valve or some structure that is moving periodically. And you could even over time map out those oscillations, and you could figure out what the period of oscillation is, right? How often this is moving, what the deflection is, peak to trough. If it's, excuse me, if it is consistent over enough time. And again, this is used with a single beam, which means you'll be activating a single piece of the crystal.